Hello, I'm Tim Pearce.
And hi, I'm Juliet Carter.
We are both software engineers in BBC Research and Development, where we look at what our audience experiences might look like in the future. For the past few years, we have been part of a large team looking at the challenges of how we allow our audiences to access exciting new immersive interactive experiences. We have followed WebAssembly from the beginning, and we are excited to be sharing our current and future research plans with you, the WebAssembly community, for the first time today. I'm going to start by discussing our problem space. What are our challenges? How do we think WebAssembly is going to solve these? I'm going to pass to Juliet, who's going to talk about how we built our WebAssembly multimedia runtime. Then I'm going to go into what the next steps in our research are. The BBC is the world's leading public service broadcaster. We're impartial and independent, and every day we create distinctive world-class programmes which inform, educate and entertain millions of people in the UK and around the world. We do this through our traditional broadcast television and radio services, and through our digital services such as the BBC website, and our native applications such as our flagship video-on-demand application, BBC iPlayer. As a public service broadcaster, one of the unique technical challenges we have as software developers is ensuring universal access to our services, that every member of the audience can access every experience, regardless of what device they have at home. In BBC R&D, we are exploring what future audience experiences might look like. Experiences which are more personalised, interactive and immersive. We'll call this new range of experiences object-based media. Object-based media allows the content of programs to change according to the requirements of each individual audience member. The objects refer to different assets that can be used to produce a piece of content. These could be large objects such as audio and video used in a scene in a drama, or small objects like an individual frame of video, a caption, or on-screen graphics. By describing how a piece of media is broken down into separate objects and attaching meaning to them, describing how they can be rearranged, a program can change to reflect the context of an individual viewer. We think this approach has the potential to transform the way content is created and consumed, bringing efficiencies and creative flexibility to production teams, enabling them to deliver a personalised BBC to every member of our audience. We have created a number of content experiences which demonstrate the advantages of object-based media, including augmented and virtual reality, branching narrative stories, and multi-device immersive audio and video. Many of these future experiences can be viewed on the BBC Taster website, but not yet on iPlayer. However, this range of future-facing content leaves us with a number of challenges. How do we give every audience member access to these experiences when they might not have the most up-to-date hardware at home? Secondly, how can we distribute these new experience formats when they could be offered in a variety of new content production tools? And thirdly, how do we get the best performance from devices in homes in a secure, sandboxed way? Well, we think that WebAssembly provides the perfect solution to the challenges that we face. And in this presentation, we're going to talk about some of the reasons why we think it's a great fit for our requirements. Currently, the BBC's flagship on-demand product, BBC iPlayer, has multiple codebases for different platforms: iOS, Android, responsive web, smart TVs, and there's very many more codebases out there to support legacy devices. While sharing a common backend, the client application is written in a completely different platform-specific technology stack, which poses a challenge to introducing new features. As a research and development team, we are looking at how iPlayer might need to adapt to fit new content experiences in, which presents an even greater integration challenge. We wanted to allow our audience to be able to select an advanced, immersive, interactive experience that's object-based from the carousel of iPlayer, much like they would do the latest episode of something like Doctor Who, and dive straight in without having to install a new application. These different types of object-based media programs require different capabilities, and we want to make these available across as many platforms as possible. By selecting a program from the carousel, the application no longer has to just initialize the video player. It has to have the ability to load up new capabilities for that application, such as rendering an immersive interactive scene. WebAssembly allows developers inside and outside of the BBC to offer individual experiences in a language and tools of their choice, such as a games engine, and produce a universal binary which is both performant and sandbox from other experiences running on the platform. You can imagine that this turns the iPlayer interface into something a bit more like the launcher on an operating system. In many ways, object-based experiences can be considered to be software, which means the BBC will have to adapt its infrastructure to deliver software alongside video. I'm going to pass you over to Juliet, who's going to talk about how we created a multimedia WebAssembly runtime for iPlayer.
Thanks, Tim. So to see how WebAssembly could help us with some of the challenges that we face around distributing experiences to all members of the audience in a secure way, we wanted to see if we could run a service like BBC iPlayer as a WASM module. So just as a note, we use iPlayer throughout this presentation as an example of a multimedia application that people might have heard of, but this really could be any sort of application with multimedia functionality. So as Tim said, we've got to address the challenge of universal access, which is to play back any multimedia experience on any audience device, and we're trying to do so sustainably, which means trying to write an application once and being able to run it anywhere. So in the last 2-3 years, this is the journey we've been on to get to the point where we can write an app once and where we can run it anywhere. So if we take BBC iPlayer as an example, we have at the moment a JavaScript code base for responsive web apps, another JavaScript code base for smart TVs, and a separate code base for native mobile phones, for example using Kotlin for Android. And all these create separate binaries for all their target platforms. So then we explored the idea of one code base which would create multiple native binaries. And this is what we'd worked on in the last couple of years. We'd created an example app based on iPlayer, written in C++, and I'll talk more about that app in just a moment. But the idea was being able to run multimedia applications from one C++ code base on lots of target platforms. And this is actually when we first started working with WebAssembly. We were able to run our C++ iPlayer app on all the major browsers by compiling it to WASM using Emscripten. And from the same code base, we'd also be able to compile the app natively to macOS, Linux, Android, and Raspberry Pi. And the next step, number 3, which is the focus of this presentation, is one code base gives one universal binary, and that binary can run on lots of different target platforms. And this is when we turned to native WebAssembly. Could we compile our C++ iPlayer app to WASM and have it run as a WASM module on all our target platforms? So we'd done that on the web already, but we wanted to target native platforms as well. So I'll take you through the work we did to get our multimedia application working as a native WASM module. So to do that, we had to have our application that would compile to WASM and then build a native WASM runtime capable of playing back the application. So as we mentioned before, we chose our example multimedia application to look like a version of BBC iPlayer, which is the BBC's content provider service, so that it would allow users to select content to play back. But we wanted a multimedia application to demonstrate certain capabilities beyond traditional video playback. So we implemented a few interesting features. Our player is of course able to play back video, but it can also allow users to play back object-based media experiences. And so for that reason, we've called our application the Single Service Player, or SSP as I'll refer to it in the rest of the presentation. So the SSP is written in C++, and as I mentioned, we've been developing it and compiling it natively for a number of target platforms, including already using WASM for web platforms. But having our codebase in C++ meant that we could also use tools like the WASI SDK and the Clang compiler to compile the SSP as a WASM module and run it natively. So just to add a little bit more detail as to what we implemented as part of the SSP, I just wanted to show some of the features that the SSP has that we needed to compile to WASM. So I've included some short clips of the SSP just as a little demo. So we implemented things like a dash player, which would enable playback of normal video. We also implemented an object-based media story engine, which can play back experiences such as branching narratives, which are produced by our creative content teams. And playing back these interactive experiences is something that was actually only previously available on web applications. So we've integrated that as part of our iPlayer application. So as you can see, users can skip pieces of content and just make choices as to what they want to see.
Do I explore the cave or do I look behind the tree?
And we've experimented with remote streaming as well, running high-end graphical experiences in the cloud, sending user inputs across the network and streaming the resulting scene as video on the client device. So here my colleague is interacting with the scene which is actually rendered remotely on a cloud. So this is the application we wanted to compile to WASM from our C++ codebase and run in a native WASM runtime. As you can imagine, there's quite a few considerations that needed to be taken care of when compiling the SSP. It makes use of a lot of low-level multimedia functionality, which utilises some of the platform's hardware resources. So, for example, we need some windowing and rendering capabilities, as in most cases multimedia applications have graphical elements to it. So in the case of the SSP, we are rendering a UI screen and some video frames in a window. But we also need to use the platform hardware to identify user inputs, like keyboard or mouse interactions, so users can navigate the UI or a scene in the remote rendered experience, for example. And as for media, we need to be able to decode some audio and video content, and using the host's hardware resources to do this is much more efficient than just doing it purely in software. So these multimedia functionalities are of course not supported by the WebAssembly specification, and there is currently no WASM runtime that offers these capabilities, which is why we've decided to build our own. So we started by identifying all the low-level multimedia capabilities that couldn't be compiled to WASM because of requiring platform-specific implementations, and we pushed them down into the runtime, which of course is itself a native application. And the question was then, how do we make the multimedia capabilities, which we'll implement in the runtime, accessible to the WASM module? And we can do that simply by passing a bunch of imports into the WASM module from the runtime. So this diagram shows kind of what we wanted to implement in terms of the runtime and how our WASM module interacts with the runtime to have access to these low-level multimedia capabilities. So let's do a step-by-step walkthrough of the design and implementation for this. So when deciding what sorts of imports to pass into the WASM module so that it could have access to the low-level multimedia capabilities, we looked into WASI, which defines a set of APIs to allow WASM modules to have access to low-level host functionality, and they are passed as a set of imports and implemented in the runtime. So our approach was essentially, can we do what WASI did for file handling and networking, but do it for multimedia functionality? So we defined a portable multimedia API for our low-level multimedia functionality. And in doing that, we learned quite a lot about designing imports, especially as it's the interface between a host and a WASM environment. So for example, we had to ensure that our API was thread safe. Our host platform would usually be multi-threaded, but the WASM spec only defines single-threaded behavior so far. So we had to make sure that all worked, and we also had to make sure that our multimedia imports were memory safe as well. And using a multimedia import API, we were then able to compile the SSP C++ code to WASM, and for that we used Clang and the WASI SDK. So once we had our SSP WASM module, which would call our multimedia imports, the next step is to make sure we can run it. And so that involves creating a runtime with a few components in it. We chose to write our runtime in C++, mainly because our cross-platform code base was already written in C++. So one of the components in the runtime was WASMtime. I'm sure you've all heard of it. It's a Bytecode Alliance project, and it offers a WASI-compliant implementation of a native WASM runtime. So we used WASMtime to provide the functionality of loading and executing the WASM module. And as I said, we chose a runtime to be written in C++. So we embedded WASMtime as a C++ library linked into our runtime executable. The second component of the runtime was, of course, the implementation of all the low-level multimedia functionalities we needed our WASM module to have access to. So essentially, the implementation of our multimedia API. So for that, we'd created, over the past couple of years, a comprehensive library of cross-platform multimedia functionalities written in C++. That library sits behind our multimedia API, and it enabled us to do things like handling of user inputs, so we support keyboard, mouse, touchscreen and joystick interactions, fast decoding of audio and video streams, and rendering of UI and video frames in a window. And we were able to do that across a number of different platforms, and these are native Linux, macOS, Windows, Raspberry Pi and Android. But as I mentioned before, we'd also been able to run the SSP as a WASM module on the web with a JavaScript runtime. So our cross-platform multimedia library also supports major browsers. So we've got WASMtime that loads and runs the WASM module, and we've got the cross-platform multimedia library that offers low-level media functionality. So what we're missing now is the glue code to bring it all together and let WASMtime be able to give the WASM module access to these multimedia functions. So essentially, what we need now for each multimedia import is to create a WASM import function, call the relevant multimedia function from a library in its callback, and pass it as an import to the WASM module through WASMtime. So at this initial stage in the work, we had quite a few functions and our API was still evolving. So we wanted to create some sort of tooling that would automatically generate the function definition, callback, and the linking of it to WASMtime from our multimedia library C headers. So for that, we had a C parser that would identify the syntax tree of our C headers, translate the C types of the function parameters into WASM types, and from that generate the required code for the runtime. So this is essentially the WASM module and the runtime that we needed to run a multimedia application as a native WASM module. So the result of it is it works. We had a working WASM module in a WASM runtime, and we were able to target both web and native platforms using WASM, which is quite exciting. So our app runs in HD resolution at 60 frames per second. And because it is one code base, we're able to make it look the same on every platform just by writing it once. And when running the app on the web, this is actually a very attractive technology because it means we don't have to rely on CSS. And it has predictive behavior across all platforms as well, which makes it much easier to debug as well. Of course, there are always limitations to the work. WebAssembly at the moment is a single-threaded environment, and we've written our app so that it can work in single-threaded environment as well as multi-threaded. But it does offer smoother user experience in multi-threaded environments, so hopefully we've got that to look forward to in the future. And in some applications, especially applications that might require a lot of computational resources, the CPU can sometimes just not be enough. And so it would be great to be able to harness the computational power of GPU resources available on the hardware as well, and do that through WebAssembly. And before I pass on to Tim to tell us what comes next for us, I'll quickly summarise the work we've been through. So we wanted to investigate running a multimedia application as a WASM module natively. And so for that we used our C++ multimedia application, the single service player, which we compiled to WASM. And we also implemented a cross-platform runtime for it. So the aim of these investigations were of course to see if we could use WebAssembly to achieve our goal of universal access for future types of experiences. So get our audiences be able to access any experience on any device, and doing that by only writing the code for the application once. So that's it from me. Thanks for listening, and I'll pass on to Tim again.
So now we have experimented with running our single service player in a WebAssembly runtime, where do we go next? Going back to our original challenge, what if we wanted to give our audiences access to a photorealistic, real-time rendered experience that's personalised to them? Could WebAssembly help with that? For example, an episode of His Dark Materials where the on-screen demon could change based on the viewer's personality. Unfortunately, a WebAssembly runtime would still be limited by the capabilities of the hardware the audience member has at home. However, as WebAssembly can run on multiple platforms, what if we broke down the universal binary and ran it across multiple machines, distributing the computation and rendering? That way, the rendering and other computational tasks that make up the experience could be performed on more capable devices, such as a machine with a high-end GPU that supports ray tracing, or a machine with a neural processing unit to perform real-time machine learning. This could allow audience members to leverage other devices that they have in their homes to deliver the on-screen experience. Where these devices are not available, we would provide them access to machines in our scalable cloud infrastructure. We're also seeing a trend towards edge computing, where the rollout of superfast, low-latency 5G networks is introducing access to compute that's closer to our audiences. We are calling this new way of delivering programs flexible compute. We are currently evaluating various software platforms which use WebAssembly to do distributed computation, especially for rendering. If you know of any that might meet our requirements, please do get in touch. Our next task is to work out how WebAssembly might fit into the content production pipeline and what kind of experiences we want to enable. What tools will content producers inside and outside the BBC be able to use to create experiences for our new object-based iPlayer? For example, how can we author interactive experiences in game engines such as Unity and Unreal and run these on a future flexible compute platform? We believe WebAssembly will be an integral part of the broadcast chain of the future. Thank you for your time. If you have any questions, please ask in the Discord channel.